Hello, my name is Lucas, and I will introduce you to our work on active Visuo-Haptic object shape completion, created together with my colleagues Lundell, Behrens, Kyrki, and Hoffmann. Shape completion, that is reconstructing the shape of an object based on incomplete sensor information, is an active research problem with many potential applications in medicine and robotics. To date, most methods have reconstructed objects from only visual data, including RGB images, depth images, or point clouds. The main drawback of visual data is that it is incomplete at the object self-occlude. That is, only the front side is visible from a single viewpoint. A straightforward approach to combat the uncertainty is to gather additional data of the unseen object parts by touching the object and then reconstructing the object shape from combined Visuo-Haptic data. However, current Visuo-Haptic shape completion methods use heuristics to choose where to explore the objects or require an impractical number of touches. We combat these issues in this work with ActVH, a data-efficient, iterative, closed-loop active Visuo-Haptic shape completion method. First, a depth image is used to construct an initial point cloud. Then, a deep implicit surface network IGR generates possible shapes reconstructions. The discrepancy between the reconstructed shapes is then used to form a single voxel grid with uncertainty. The voxel with highest uncertainty is selected for haptic exploration, adding a new point to the object representation. We experimentally validated ActVH in simulation and in the real world. To evaluate in simulation, we developed our own Visuo-Haptic robotic simulation environment with the Mujokov physics simulator. We compared the reconstruction accuracy of ActVH on 35 objects in the simulation and on 10 objects with various shapes, sizes, and weights in the real world. The experiments were carried out on Kinova Gen 3 robotic arm equipped with a custom-made finger to perform haptic exploration and with a robotic two-finger gripper. The arm is equipped with joint torque sensors in each of its joints, which allowed us to detect collisions with the objects in both the simulation and in the real world. The simulation environment, all data and code is publicly available and can be used as a benchmark. We compared our reconstructions to 5 baseline methods shown in the figure. ActVH provides the most realistic and watertight matches of the whole object. The other methods provide an incomplete meshes or meshes with sharp, unrealistic edges. In addition, our method is able to provide usable results even for adversarial objects, such as the transparent bottle. We evaluated the reconstruction against ground truth matches using the chamfer distance, where the smaller value the better, and using Jacquard's similarity, where the bigger value the better. Each reconstruction was repeated 3 times for each object, resulting in 105 reconstructions per method in simulation and 30 in the real world. In the simulation experiment, we further compared ActVH to a random policy that touched the first reachable voxel from the set of uniformly sampled voxels on the surface of the reconstruction and to a GPI-driven policy, where the voxels with the largest standard deviation was selected. The result shows that our method, which is marked with the red colors in the figures, overperforms the other method with a notable margin. In addition, ActVH shows increasing accuracy with increasing number of touches. The final experiment evaluates the impact of ActVH on graph success rate. The objects used are shown in the figures. We decided to benchmark ActVH against the convex hull method because it reached the second best reconstruction accuracy in the previous experiments. Possible graphs were sampled and grasped. The results indicate that ActVH performed better than or on par with convex hull on all objects. Thanks for your attention.